Hi, and welcome to our second video on the laws of logarithms and exponents. In this video, we're going to be focusing on solving equations using the laws that we looked at in the first video. So let's go. All right, so here's our first example using the laws of logarithms and exponents. And I'm going to actually invite you guys to put your video on pause right now so you can work it out on your own and then come back and compare it to the solution that I'm about to show you. So if you take a look at our problem in front of you, you may have solved this one way, and I'm going to actually show you a way of solving this that doesn't involve the law of logarithms at all. I'm actually going to use the law of exponents to make these bases the same because I can. So you'll notice over here on the left-hand side, I have 2.5 in brackets, and it's to the exponent 2 plus x. So my exponents are being added. Then on the right-hand side, I have a 10 in brackets. The bases are the same. So these are the two I actually want to make the bases are different. So I want to make them the same to be able to solve this. And the way to start that is to take those exponents that I added, and I'm going to convert that into a power of products on the left. And on the right-hand side, you can see where I've taken my 10 and I've made that into factors of 10. So in doing so, I've created the common base of 2.5, and I want to keep that through the rest of my problem. Next, you see me just applying the exponents. So my 2.5 exponent 2 works out to be 6.25, and I've kept my 2.5 exponent x. I can't really do much with that right now anyway. But over here, I've distributed that exponent 3 over the 4 and also over the base 2.5. Another round of multiplications, and that leaves me with 800 on the left-hand side, still keeping my base and exponent over here. And the 12.5 times 64 on the right-hand side, if I multiply that, it also gives me 800. So now I've got a situation where I have 800 on the left and 800 on the right. So my 800s are just going to cancel out. And I'm left with that common base that I want to keep, that I wanted to keep so badly right here. So I have 2.5x on the left, and I have 2.5 to the exponent 3 on the right. Because these two sides are equal to each other and the bases are common, then I can just say that x is equal to 3. And I have my solution. So you don't always have to use the law of logarithms. Sometimes the law of exponents will do. And if you really want to, you can go back and just double check your answer by plugging it back in where x is equal to 3 and just seeing if the left side does actually equal the right side to make sure the problem works. But that's not really mandatory. So in our second example, we actually need to apply the laws of logarithms to solve this. You can see here that I've got this 20,000 out front, and my first step is really just to get this whole thing into exponential form. So in order to do that, I'm going to start by dividing that 20,000 out of there. So both sides divided by 20,000 leaves me with the exponential form that I want. From the exponential form, I'm going to have to put this into logarithmic form. So remember that when you convert from exponential to logarithmic form, the base remains the same. So base of the exponential form is the base in the logarithmic form. The power in exponential form becomes the argument in logarithmic form, and the exponent becomes the answer to the logarithm. Now, I also notice that on the right-hand side, I have this x, and this is ultimately what I want to solve for. But my calculator is really not going to like that base of 0.8. So this is where I want to apply the law of change of base in order to make my calculator happy and be able to solve for that x. So when I apply that law, I end up with this scenario. And you'll notice on my left-hand side here, I haven't actually written my base in. If you recall from our first video, that means that I'm using the base 10. We don't need to write base 10 in. Now my calculator can handle this situation. So type the left-hand side into the calculator, and I get 4 as my answer, which leaves me with a really simple equation to solve. I just have to go about and isolate my x. Because my entire right side is being multiplied by 2, that means I can divide the left and right side by 2 to get rid of that 2, leaving me with 2 is equal to x minus 5. Last step is just to add 5 to both sides to get rid of the 5 on the right-hand side. And so my answer ends up being x is equal to 7. And I'm done. All right, so for our third example, again, we have exponential form that we're going to have to convert into logarithmic form. Before I go ahead, though, I just want to point out I can actually use either of those two bases. In other words, when I convert to logarithmic form, I can use my base 3, or I can use it in terms of base 5. Every step it's going to look different, but ultimately the answer would be the same. In the example that I'm going to propose to you guys, I'm actually going to use the base 3. So putting it into logarithmic form, this is what I get. And I can see that I actually have to use my laws of logarithms in order to go forward. So that exponent x here is going to be pulled out front. And now I have x log base 3 of 5 is equal to 2 plus x. I already know my calculator is not going to like dealing with the base 3. So I'm going to use the change of base law to put it into a base of 10 to give me this scenario. So now I can actually get a numerical value where log base 10 of 5 divided by log base 10 of 3 will give me 1.465x because of the x that was here. Remember, that isn't forgotten. And that's approximately equal to 2 plus x. Solving for x leads me to this. So I just got to bring that x over to the other side. So and then I subtract my like terms to give me 0.465x approximately equal to 2. When I solve for x, I'm left with x is approximately equal to 4.3. And I'm done. So for our next example, we're actually going to go from logarithmic form into exponential form. So in order to do that, the first thing I notice, though, is that I've got a 4 out front, and I want to get rid of that. So I'm going to divide by 4 on both sides before I go any further. To get my logarithm, log base 2 of a product is equal to 8. That product, I can actually split that up. So I'm going to end up here with log base 2 of 8 plus log base 2 of x plus 3 is equal to 8. Now, the log base 2 of 8, that's pretty easy to solve mentally. So I don't even need my calculator to do this. I just need to think about, well, what exponent do I put on the 2 to give me 8? And of course, the answer to that is 3. 2 exponent 3 gives me 8. So I'm now at 3 plus log base 2 of x plus 3 is equal to 8. Can subtract 3 on both sides, and I've isolated my logarithm. Now here I run into a bit of a bug because I can't actually solve this with the x there. So I'm going to actually put this into exponential form to finish my problem. In exponential form, this is what it's going to look like. So remember that my base in logarithmic form remains my base when I put it into exponential form. The answer to my logarithm becomes my exponent, and my argument becomes my answer. So I have 2 to the exponent 5 is equal to x plus 3, which is, of course, the same as 32 is equal to x plus 3. When I isolate my x, I get x is equal to 29. So you see, if you can't solve it using logarithmic form, put it into exponential form, and it should go better from there. All right, so now I've got a final example here where we're going to have to apply our laws of logarithms and exponents. And I'm going to invite you guys all to put your videos on pause for a moment and try working it out yourself. And then you can come back, of course, and compare to the solution that I'm about to show you. So to start it off, I want to look for like terms here. And I can see already that I have 3 log base 3 of 6, and that is actually a like term with negative 6 log base 3 of 6. So I'm going to combine those two together, and that's going to give me negative 3 log base 3 of 6 that you see here. For now, I'm just going to leave the 4 log base 3 of 1.5 alone, but you'll notice that I suddenly have this positive 7 log base 3 of 2. Well, that actually comes from this right here. So I'm just going to put a little box around that, okay? This negative 7 log base 3 of 1/2. If I apply the exponent laws to that, that leaves me with negative 7 log base 3 of 2 to the exponent negative 1. So my exponent negative 1 is, of course, going to come down and multiply by that coefficient negative 7. Negative 7 times negative 1 gives me the positive 7 you see here. So it's a little easier to deal with. Now, my log base 8 of 1, that's actually coming from this here, that logarithmic expression there. If, of course, 8 minus 7 is going to give me 1. So I've just gone ahead and done this subtraction, and that's why you see just 1 there. For now, I'm going to leave my negative log base x of x alone. I'll come back to that in a minute. All right. So for the next round, what you see here is basically those coefficients are going to come up and become exponents on the arguments. So in the first case here, we're going to leave the negative out front, but I do take the coefficient 3 and I'm putting it on the argument 6. So now I end up with 6 exponent 3. I'm going to repeat the procedure over here to end up with 1.5 to the exponent 4. And again over here, that leaves me with 2 exponent 7. You'll also notice that I went ahead and I dealt with the log base 8 here. Anytime you have the log of 1, regardless of the base, the answer is going to be 0. So that's why this 0 is right here. And I also took care of this logarithm here. You'll notice that the base and the argument are the same, and you may or may not recall that when the base and the argument are the same, the answer is 1. So this is why we now have negative 1 here. All right. Because I have these logarithms with base 3, I can actually apply my product and quotient rules to end up with this result. And you can see that because these two terms, these two logarithmic expressions were being added, they actually stay on top in the numerator position. Because this one was a negative term, it becomes the denominator. So what I end up with is the 1.5 to exponent 4 that you saw earlier here, multiplied by 2 to the exponent 7 in our numerator position. And in the denominator position, we have the 6 exponent 3. I, of course, can get the numerical value of that expression, so I'm going to go ahead and do that. And I end up with log base 3 of 3 minus 1. Of course, when I have a base and an argument that are the same, my answer is 1. So ultimately, what I have here is 1 minus 1, which is 0. And I'm done. So this concludes our second video on the laws of logarithms and exponents. I hope you guys enjoyed it. I hope it helped you. And I hope that you also take a moment to go check out the practice problems that are associated with this topic. Until then, see you next time.